Okay, so welcome to lecture 35. So as we talked about yesterday, we are going to discuss today linearized theory of thermoelasticity. Okay, so all the equations that we have till now, it's a nonlinear equation which is going to hold for large deformation. Okay, now today we want to linearize those equations in the unknown displacement. So let me, for example, write to you one of the equations, that is linear momentum balance. So according to that, divergence of first polar Kirchhoff stress tensor plus I guess we have rho naught here. Maybe somebody can tell me, plus body force is equal to rho naught times acceleration. I think, okay, so there is a J here. Yeah. Right, so this is the equation of linear momentum balance. Now, if we look at the right hand side, then we ask, is it linear or non-linear in the displacement? Then what will be your answer? Rho naught, for example, is it linear or non-linear in the displacement? Anyone? Yes. Is rho naught linear in displacement or non-linear function of displacement? So Vishwas says it is non-linear as J is there. So recall, what is rho naught? Rho naught is mass per unit volume in the reference configuration. As the deformation occurs, what is happening to rho naught? Is rho naught changing? First of all, mass of the body is fixed. Volume in the reference configuration is fixed. So mass per unit volume in the reference configuration does not change. So rho naught is not a function of displacement at all. So it's a constant. Okay, so it acts like a constant. That's for rho naught. What about acceleration? Is it linear or non-linear in displacement? Let us suppose we are looking at, this is a Lagrangian viewpoint. Try to think of its expression in terms of displacement and see what is the degree of that expression in displacement. If it is u square or u cube or logarithmic of u, sine of u, it's all non-linear. If it is just u, then it becomes linear. Okay, Toiva says it is linear. Any different answer? So yes, it is linear. So acceleration, its expression is del to u as a function of x comma t over del t2. So you can see this is linear in u because there is no power of u present here. The power of u is 1. So it's linear in u. So this is, so the right hand side, it's a constant times linear term in u. So overall it becomes a linear. So we don't have to do anything for the right hand side. It's already linear. Okay. What about this one? J times B. Supposing that B is a constant, okay, but that can also often this body force B can also depend on displacement. For example, we were thinking no, that suppose you have moon and earth system and moon is moving in the space, then as the moon moves in the space, the distance between moon and the earth is changing, therefore the gravitational force is also changing. So B in that case will become a function of displacement of the moon. But there are for real life examples, for example when you're analyzing any machine on earth or any deformable body you're analyzing, let us say a table. So for them, the gravitational pull, acceleration due to gravity, we treat it as a constant. So B becomes a constant in that case. Okay. So I'll say often it is constant, but need not be always. But let us say for now that it is constant. Then what about J? Is it linear or non-linear in displacement? So J is non-linear in U, right? Because J is determinant of F, which is determinant of identity plus gradient of U. And many of you have worked it out that it is same as 1 plus trace of U. This gradient is Lagrangian gradient, obviously. 1 plus divergence of U plus higher order term in displacement. So it's a big O, right? So if you want to linearize this, you have to just say it is equal to approximately equal to 1 plus divergence of U. Okay, so if you want to work with a linear equation, then you have to approximate J with 1 plus divergence of U. All right. Now let's look at the first term then. What do you think about this? Is this linear or non-linear in displacement? Okay, so Minel says it is linear. So Viswas writes this is equal to rho naught del psi over del f. Yeah, so let's explore it. So P equals rho naught del psi over del f. And if if you think of writing this in terms of satisfying objectivity, think of psi which satisfies objectivity, then it's actually 2 rho naught f into del psi by del c. We want to work with this expression instead of this because we will be ensured that it will satisfy objectivity with psi being a function of c. Although you can work with first one also, but you have to be careful that you choose a psi such that it does not violate objectivity. So now what do you think? Is it linear, non-linear? It all depends on the function psi. What kind of function this is? Is psi linear in f? So can you have psi as, for example, f double contraction identity? So this, is it a possible function for psi? Is it possible? Anybody? So how do we check that? We have to see that it ensures objectivity. So do you think it will satisfy objectivity, this formula for psi? Okay, so Vikram says it will satisfy objectivity. Anybody disagreeing with this? See, for it to satisfy objectivity, psi of f must be equal to psi of qf, right? So this, if psi has this function, it must be equal to qf double contraction identity. Now, do you think this is going to hold, that these two will be same? So it is not same. You can work out and show that it is not same. So such a function for psi does not satisfy objectivity. Okay, that's why it is very tricky when you try to write down an arbitrary function for psi in terms of f. But when you can work with an arbitrary function for psi in terms of c, as far as satisfying objectivity is concerned, you don't have to bother about it. Any function of c will always be objective. Now, can you tell me this formula for p? Let us say if we are working in terms of c, is this linear or non-linear in displacement? So if I work it out more carefully, it becomes 2 rho naught into identity plus gradient of u. So f is linear in displacement, right? Because as you can see, it is identity plus gradient of u times del psi by del c. Okay. Now this is where things start to become non-linear. It all depends on what kind of function you have chosen for psi. Okay. And it turns out psi is at least quadratic in C, because for example you always work with energy, spring energy, for example, it is half kx square, so it's quadratic, so that when you take the first derivative it becomes linear. So psi is usually at least quadratic, and therefore the first derivative is usually at least linear in C. That's the usual thing. Okay. So if this is at least linear multiplied by something which is again linear, then you get it to be quadratic, right? So therefore this expression for P is certainly um, non-linear. So if you want to linearize this, you can certainly approximate it as 2 rho naught del psi over del c. Or let us say if I expand it, it becomes 2 rho naught del psi over del c plus 2 rho naught gradient of u into del psi by del c. Okay. Now you can see that this term is at least quadratic. So you can then forget about this term and just have the first one. Okay, because we want to forget about higher order terms in displacement. And if you then think of sigma, what is sigma? So sigma is 1 over j times p times f transpose, right? So that is then 2 rho naught f del psi over del c into f transpose. Now let us try to linearize this. This you'll then get, okay, and there is I think 1 by 1 by j also present, 1 by j. So if you try to linearize this, what you have to do is you have to write each of the terms in terms of displacement. So you had 2 rho naught, then f is becoming identity plus gradient of u times del psi by del c times identity plus gradient of u transpose times 1 by j, and j we just saw that it is 1 plus divergence of u plus higher order term, right? And then you have to take 1 to the power minus 1 because it was in the denominator. Okay, this is a fully expanded expression in u, and you should actually also do it for del psi by del c, but we know that it is at least linear. Okay, so then this becomes 2 rho naught. If we try to keep the term which is just linear, then you will have to, one of them will be 2 rho naught del psi by del c. See, this thing becomes 1 minus divergence of u plus this higher order term. And then when you cross multiply, when you multiply each of the terms, then one of the things you will get is 2 rho naught del psi by del c, and rest all will be higher order. So what you see is that when you linearize the expression for P and sigma, then both of them become the same. Okay, so that is why we say that, you know, in linear theory of elasticity, all the expressions of stress tensor, they become the same. All the stress tensors become the same, whether it is Cauchy stress tensor or first Piola-Kirchhoff stress tensor or second Piola-Kirchhoff stress tensor or Biot stress tensor. There are so many. They all become the same in linear theory. And that is why in undergraduate course, where we just work with linear theory, we are only taught about Cauchy stress tensor. But when the deformations are large, all these stress measures, they become different. So having seen that S and sigma, they both become the same when you're working with linear theory. So let's just work with, we can work with S also. So let's work with this expression for S, which is, this is the full non-linear expression, no? 2 rho naught F del psi by del C. And it's a function of C as well as theta. So let's really work it out more nicely and see what we get. So first of all, if you want to linearize this, any Taylor's expansion, you have to kind of do Taylor's expansion. So the first term will be the constant term, which you get when displacement is 0. And you see, we have to linearize this in C as well as theta. So you have to think of some reference values for C and theta. So what will be the reference value for C? We are trying to linearize in displacement. So the reference value is when displacement is 0. And when displacement is 0, what is C equal to? Identity, right? See, what I'm trying to do is, if you have a function f of x, and let us say I want to do Taylor's expansion about x equal to x naught, then the first term is f of x naught. Then you have f prime of at x naught into x minus x naught. plus you have to keep going, right? So we want to do similar thing over here. And the arguments here are both C and temperature theta. So you have to first choose a reference value for the argument. Just like here, the reference value is x naught. So here we have to choose a reference value for the argument. And the reference value would be when displacement is 0 and when theta is equal to some reference temperature theta naught. Okay, so when u is equal to 0, so that's the reference state. So I want to linearize this about the reference state or about the reference configuration. That is when u is equal to 0 and theta is equal to theta naught. Now u equal to 0 implies f is equal to identity and c also becomes equal to identity. Okay. So when we substitute it over here, the first term, it will be like s at f equal to identity, comma theta equal to theta naught. So that's the first term. Now, what will this be equal to? Looking at this formula for S, it then becomes 2 times rho naught because rho naught is independent of deformation or temperature. And then big F, you are going to write this at identity times del psi by del C, but evaluated at identity, comma theta naught. So that is your S naught. So that's a constant term. So this is like this term over here, f of x naught. Then what will be the next term? So obviously we have to kind of take the derivative of the full expression for at once time with respect to c and then again with respect to theta. Now, the other way would be, why don't we do Taylor's expansion of each of the individual terms and then kind of multiply them together? That is another way to go ahead. And that's what the book is doing. So what I'm saying is, write S as 2 times rho naught. The Taylor's expansion of rho naught is same as rho naught because it is not changing. Then for big F, it is crystal clear. It is identity plus gradient of u. So it stays, it remains there. There is no higher order term. This is the exact expression for big F. Then comes del psi by del C. So here we have to do the Taylor's expansion. So this will have the first term del psi by del C at C equal to identity, comma theta equal to theta naught. That's the first term. Then you'll have second term as del 2 psi by del C into del C. Okay. Evaluated at C equal to identity, comma theta equal to theta naught. And then multiplied with, see, this has to be then multiplied with C minus identity. This is the analog of x minus x naught. So you have to have your C minus identity. Okay. Plus del 2 psi by del C del theta into theta minus theta naught. And then you have higher order terms, which you can forget about. Is it good for everyone? I hope that you guys are able to follow this. Now, what is C minus identity? Let's also try to work it out because I want to write it in terms of displacement, no? So C minus identity. So C in terms of displacement is identity plus grad U plus grad U transpose plus grad U transpose into grad U. So that's your C. So C minus identity, then you can see that it is this thing. Okay, and we can therefore plug this thing over here. Now try to retain the terms which are linear in displacements and neglect the things which are nonlinear. So first of all, we have to think of the constant term. The constant term is going to come from when you multiply this thing with identity and further with this. That will give you the constant term here. So that's the first term, just 2 rho naught del psi by del c times, so del psi by del c, and evaluated at c equal to identity, comma theta equal to theta naught. Which is the next term. So the others will be linear in displacement or theta. So what are those terms? So that you will get by, for one of them is, for example, 2 rho naught times grad u times this. So this is something which is linear in displacement. Another linear expression is 2 rho naught times identity times this thing. So let us first write down the green one. Okay, so if I write on the green one, it's going to be plus 2 rho naught times gradient of u into del psi by del c at c equal to identity, comma theta equal to theta naught. Okay, then if I think of the pink one, that's plus 2 rho naught into identity into that thing over there, del 2 psi by del c del c. You see that it's very interesting term. It's a fourth order tensor. Fourth order tensor. And this has to be evaluated at c equal to identity, comma theta equal to theta naught. So this derivative you have to evaluate in the reference state and then multiply with grad u plus grad u transpose only. You have to forget about this term because it is quadratic. Is there any other term which is linear? So unknown here is displacement as well as theta. So can you tell me, is there something which is linear in the displacement or theta that we haven't written yet? So there is one term, I can notice it. So if I use different color, yeah, maybe I can use this color. So that's going to be 2 rho naught into identity into the last term over here. Yeah, so Manoj was right. It's the last term. So that, let me write that here, 2 rho naught into del 2 psi by del c del theta evaluated at c equal to identity, comma theta equal to theta naught and multiplied with theta minus theta naught. And rest all are, as far as linear theory is concerned, rest all are junk terms. So that is something you can forget about if you're working with linear theory. So this is the expression for S that we have to substitute in our differential equation, linear momentum balance, over here. Each of the terms here has got some meaning. Does anyone know what is the meaning of, for example, this blue term? What is this? So this is like S naught, no? S naught. The stress when the body has not deformed. Stress when the body is in reference state. What kind of stress is this? Have you guys come across this stress? Even if the body has not deformed, you still have a stress in the body. Can you have such a stress? And what do you call it? Residual stress. Yes, Viswas is right. Not Piola, this is residual stress. So if you choose a reference state, which is a stressed state, then you will have this term also present. But if you choose a reference state which is stress free, then S naught will be equal to 0. Okay? And then you see the second term, that is simply gradient of u multiplied by this S naught. Okay? Again, if you choose a reference state which is stress free, then this term will also not be present. Isn't it? Then this third term. What is this third term? This is often written as 4 times rho naught del 2 psi by del c times half of grad u plus grad u transpose. And do you know what is half of grad u plus grad u transpose? So this is the strain tensor that we work in linear theory. This is the strain tensor that we work with in linear theory of elasticity. And this is also called infinitesimal stress tensor. Infinitesimal strain tensor. Okay, let us denote this by epsilon. And this thing, which is evaluated in the reference state, this is called the fourth order stiffness tensor. Okay, so if you denote this stiffness tensor by let us say the symbol, this scripted C, 1, 2, 3, 4. There are four of them. And in index form, it is simply this C I J K L. And then it has to be multiplied with epsilon, so it becomes epsilon KL. So that is this term, this green term. Sorry, is this green or this is pink? This was pink, I'm sorry. This was pink. So this is the pink term. So that'sCijkl into epsilon KL. Can you see what is the property of thisCijkl? This is the fourth order stiffness tensor. How many constants does it have?Cijkl, how many constants does it have? Or how many terms are there in theCijkl? Anyone? 81, right? Because IJKL, each of them go from 1 to 3. So it has 81 terms. But you see, it has several interesting property because this C is actually forerunner del 2 psi by del C, no? And C itself is symmetric. So can you say that Cijkl will be same as Cjikl? So basically the Cijkl is del 2 psi over del Cij into del Ckl. Now Cij is same as Cji. Therefore, this scripted Cijkl will be same as scripted Cjikl. Likewise, scripted Cijkl will be same as scripted Ijlk. Isn't it? Because the CKL is same as CLK. Cij is same as Cji. Furthermore, due to the property of mixed derivative, this is same as del 2 psi over del Ckl into del Cij. Right? You can change the order of derivative. So that implies this scripted Cijkl is equal to scripted Klij. So it has, once it has these symmetries, and these two symmetries are called minor symmetry, whereas this symmetry is called major symmetry. So can you now tell me how many terms does it have? How many independent terms it will have now? Out of 81, how many independent terms are actually present? Anyone? If you just take into account this minor symmetry, then you see that Cij, scripted Cijkl is same as scripted Cjikl. So Ij is same as Ji, that means out of those 9 from I and J, only 6 of them are there, independent. So therefore, this will ensure that 81 goes down to 36, 6 into 6. Earlier it was 9 into 9, but then due to minor symmetry, it goes down to 36. Furthermore, because of this major symmetry, so you have now 6 into 6, but Cijkl is same as Cklij. So this 36 goes down to then 21. And I have shared with you my lecture notes from UG class. I have shown in more detail how it goes from 81 to 36 and then 36 to 21 through some matrix form. So finally, this CIJKL, this stiffness matrix or stiffness tensor, actually has only 21 independent constants. Okay. So we say that the most general anisotropic material has 21 independent constants. That is how it is coming from. Notice that as of now, we haven't used symmetry in this expression. When we do the Taylor's expansion, we just use objectivity. We haven't used symmetry yet. So without symmetry, what we are able to see is that a most general material having linear stress-strain relationship. You see, this is for linear stress-strain relationship because this pink term here has got stress equal to this stiffness multiplied by strain. It is linear. So for linear stress-strain relationship, you will have maximum of 21 independent constants. Okay, so that is a take-home message from here. And this is, by the way, only for linear elastic stress-strain relationship, purely elastic. We haven't yet gone to the thermal part. Thermal part will also have some term, no? So the last term is the last term actually, this orange term. So this is the thermal contribution. Okay, and this in the book, for example, they call this. So if I write it here, this 2 rho naught del 2 psi over del c del theta. So they call it M, tensor M. Okay, and it is also called in words. It is called second order stress temperature tensor. Second order stress temperature tensor. Okay, and in index form it is simply Mij into theta minus theta naught. So due to change in temperature, how does stress change? So that is taken care of through this term in linear theory of thermoelasticity. How many independent terms does this tensor M have? Can anyone tell me? 6. True, because M has to be symmetric. So it has 6 independent terms. So for most general material, it will require 21 mechanical constants and 6 thermomechanical constants. And if one further uses symmetry, then we know that for isotropic material, for example, this 21 goes down to 2, isn't it? So that is something we are aware of, but we haven't proved it here. So if you use further isotropy symmetry, then 21 goes down to 2. Okay. So you can see it's so much of reduction going from 81 down to 2. It's a great deal of reduction, no? Okay, and there are ways to derive it. There are so many ways to derive that 21 will go down to 2. Okay, so this was for the stress. And like I said, if the reference configuration is stress-free, if the reference configuration is stress-free, then the Piola-Kirchhoff stress tensor, Pij. Okay, I don't know why I'm calling it S. It is actually P, no? Nobody told me. This is P. So that's P. First Piola-Kirchhoff stress tensor. Okay, so if the reference configuration is stress-free, then Pij is same as sigma ij, and it is equal to Cijkl epsilon kl plus Mij into theta minus theta naught. So that is the constitutive relation, linear stress strain temperature relationship. So linear thermoelastic constitutive relation. Okay, and you know that Cijkl has got some symmetry. It has only 21 independent constants. And it is this expression which has to be plugged in your LMB, linear momentum balance. So you have divergence of P plus J times B equal to rho naught times acceleration, no? So in component form, I think it is del P Ij over del J, sorry, del Xj, am I right? Or it is del Pji over del Xj plus J times Pi is equal to rho naught del 2 Ui over del T2. And okay, I'm just going to stop here. And for Pij, you then plug in this formula. And therefore, finally, you will have an equation in terms of displacement, because this epsilon KL, remember, it is half of del UK over del XL plus del UL over del XK. Okay, so finally, you will have this equation in terms of displacement and temperature. I may ask you in the exam, what will this look like when you plug in this expression? So this is, we did only for linear momentum balance. Likewise, you can plug in these linearization, or you can linearize the energy equation also. And I can ask you that in the exam. Okay, so you should think about that. So likewise, one can also linearize the energy equation. And I'm staying here, you can ask me doubt if you have some.
Sir, from lecture 32,
Yeah.
sir, there is a material objectivity and material isotropy at the end of this lecture. Uh, that part, please uh, explain again. because I don't understand why I had Q transpose C Q, how it arises.
Okay.
This
Okay,
is
here you are saying, no, that how it becomes Q transpose CQ.
this.
So that is also quite clear. Um, so if you look at these two relation, that psi of F is same as psi of FQ, right?
Yes,
From
sir.
symmetry.
Hmm.
But objectivity says psi has to be a function of C.
Yes, sir.
So when you have F, your C is F transpose F.
Yes, sir.
And when you have FQ, then your C, which I'm calling, let us say C star, is then FQ transpose FQ, which is same as Q transpose F transpose F into
Okay,
Q.
okay, okay, okay.
And this is same as this.
Same, whatever the read at objectivity, same like here.
Right.
Sir, I have one doubt regarding the double contraction of tensors.
Okay.
So, do we have any matrix operation method also for calculating double contraction, or we always have to go to ACL form and
Okay. Matrix method. You mean double contraction of second order tensor with second order tensor?
yes, sir.
Okay. I don't think so. At least I'm not aware of.
And sir, actually, I had one doubt in lecture 25 last part, sir.
I mean,
Actually,
yeah, you can say the following. Um, so if you have A double contraction B, then this is Aij Bij, right?
yes, sir.
The same as Aij into B transpose Ji. Okay. So this is like trace of AB transpose. Slightly different. So you see this thing is what? This is AB transpose, but you have to look at II. So therefore it's a trace.
Sir, one more thing, sir. In lecture 25,
Oh, here. Okay, I represent J and J with I.
so can you explain this part again, sir?
Yeah, this is something you can always do. So because I and J are dummy indices, no? Suppose you have an expression Aij Bij. This is same as Aji Bji. Because I and J are dummy indices, you can replace it with anything, with any index. This is, sorry, with any symbol. So this is also same as Akj Bkj, where I have replaced I by J. This is also same as AKL BKL, where I replaced J by L. So if you have a dummy index, you can replace it with any symbol which is not present in the expression. So while going from here to here, I simply changed J to I and I to J, and it's still the same.
And sir, like when we move down, where we have written f dot kj is arbitrary. After that, there is one step where we wrote Tij into Fki equal to Tji Fki.
Yes.
How did we do this part?
Okay. I think we in the beginning we assumed that T is symmetric, right? That is
Symmetry, due to symmetry.
yes. So we said no that because it's the work conjugate of E and E is symmetric, so E dot will also be symmetric. So symmetric tensor double contracted with another tensor, and if that another tensor T has antisymmetric part, then it does not contribute. It's only the symmetric part of T which will contribute. So you can take T to be symmetric from the beginning. So we have T symmetric here from the beginning, and therefore in the end we said that these two are same.
Okay, sir.
Determinant of C, the del divided by del C.
Oh, you mean derivative of determinant of C with respect to C?
Yes, yes, yes. Derivative of determinant of C with respect to C.
So this is, for any matrix also, del of determinant of A with respect to A. So that's equal to det A into A inverse transpose. And this, how do I get it? I think I had shared some notes, isn't it? Can anyone confirm that I had shared the notes?
Yes, sir.
All right, so you please check the email. I have it. I have sent it.
Okay, sir.